Hi learners, it's Em from Sononerds. This video is going to be on Unit 4, the 5 parameters of pulsed sound. Up until this point, we've really just been talking about sound kind of in the abstract. We know it's a thing, you can hear my voice, there's sound in the air. We know we're using ultrasound with our machines, but what we might not know is that there is something called a continuous wave and a pulsed wave, and ultrasound actually uses both. It just is a matter of having a high enough frequency to be considered ultrasound. So in this image here, we have a continuous wave on top. You can see that it is just one ongoing wave. That is how most sound waves occur. But then we also have pulse wave, which is on the bottom. And you can see that there is a transmit time where the wave is present, and then there's an off time where you don't see a wave occurring. In this unit, we are going to cover a little bit more about what pulse waves are and what the on and the off time, all of that means. But it's important to remember that those 7 parameters of sound, frequency, period, propagation speed, wavelength, amplitude, power, and intensity, all can describe continuous waves and pulsed waves. But this chapter is going to focus on just pulsed waves. Now the important part about pulsed waves and why we use them in ultrasound is because pulsed waves are the only way an image can be created. I mentioned earlier about the transmit time and the receive time. We can refer to that as on time and off time, or talking time and listening time, but it's because of that off time that the machine has a moment to process the information coming back from the echoes and create the image information. So take a look at this image. On the top, it says continuous wave ultrasound is kind of like writing in cursive without any spaces or periods. It's all connected and there isn't a way for the brain to read the picture without time to figure out each word. Now compare that to the bottom, which says pulsed wave ultrasound sends sound energy out in bursts, just like each of these words. You can understand each quote-unquote pulse because there is a clear beginning and end. While this might not be the most clear-cut example about continuous wave versus pulsed wave, what I like about it is that it shows you that continuous wave, the top word block, is not super easy to clearly see the words. It's not super easy to see the picture. You can't really parse what it is saying without the breaks in the words, like the bottom one. So in the bottom one, we see letters that are grouped together, just like our cycles are grouped together to create a pulse. And then there's a break in between, so our brains can actually read the words and the letters as they are put together and make sense of them. So again, continuous waves do not create pictures. We can get ultrasound information back from them, we can get data back from it, but at no point will a continuous wave create a 2D picture like we commonly see with diagnostic medical ultrasound. So by having that receive time, the machine can process the information from the pulse and create an image. And just like the words are made up of letters, each pulse is made up of cycles. But the cycles are going to work as a unit and travel together. Now this is why a lot of the books use trains as an example for pulses. The idea behind the train analogy is to think of the train as consisting of a bunch of cars or cycles, but the train travels together as one unit, just like the cycles in a pulse travel together as one unit. So we had our 7 parameters that describe continuous and pulse wave sound. We now have 5 new parameters that we can use to define parts of the pulse wave. And these are going to include pulse duration, spatial pulse length, pulse repetition period, pulse repetition frequency, and duty factor. And again, for each of these new parameters, we're going to focus on the definition, synonyms, units, symbol, or really more of the common abbreviation for these, formulas and relationships, and how the sonographer can impact each parameter. Before we get into the parameters though, I think it's important that we spend some time learning how to identify a pulse and what it'll look like in our studies. So we know that this is one cycle. We've got the beginning to the peak to the trough, back to the beginning again. And when we put a non-ending string of cycles together, what we're looking at is a continuous wave. It just keeps going. When we see an image that includes multiple cycles grouped together with a clear break in between, we are looking at the graphical representation of pulses with an on time, where the cycles are, and the off time, where there is a break in between the cycles. Pulses can have many cycles, or they can have very few cycles. They can have long wavelengths, or they can have short wavelengths. The most important part though is that there is a start to the pulse and an end to the pulse, and time in between for receiving. Now the receive time is super important for creating our images because we need time to process the echoes that are returning from the pulses being sent out. but the pulses themselves are actually really important to the process as well. The number of cycles within the pulse plays a big role in the accuracy of the ultrasound image. When we are using B mode or grayscale in clinical ultrasound imaging, most machines are going to emit a pulse that has around 2 to 4 cycles in it. The shorter pulses are going to create more accurate images. Compare that then to Doppler ultrasound, which is going to require more cycles per pulse to get more accurate information. So ultimately, as sonographers, we are trying to create the most accurate ultrasound image that we can. And to do so, we need to know what creates accurate images. And so when we look at pulse waves, we know that short pulses are going to create a more accurate ultrasound image, especially in B mode imaging. Short pulses are going to be made up of fewer cycles, shorter wavelengths, short periods, and high frequencies. I know we've discussed in earlier units that the use of a high-frequency transducer is better because it gives us more detail. Well, this list actually just kind of proves our point even further. Those high frequencies result in short wavelengths. Short wavelengths are going to make for shorter pulses, and shorter pulses are going to improve our axial resolution, which means we get more detail. So I don't expect you 4 units into this course that you already know all of this, but I want to provide this list for you because we're going to keep building on it as we move through the units. I want you to have that information in the back of your mind so you start thinking and putting those pieces together. Why am I choosing this frequency, or why am I setting the machine up this way compared to another way? What am I improving when I do this? And what physics am I paying attention to? Now, another way that we can improve ultrasound images is by having short receive time. And this is especially true for those of you who are going to be working with moving objects, specifically the heart. So adult, pediatric, fetal echoes take a look at the moving heart. We want to be able to see the heart moving in as close to real time as possible. And to do that, we need to make sure that we are, again, setting up the machine appropriately to achieve that real time imaging. Now we're going to discuss this quite a bit more when we get to our frame rate unit. I believe it's unit 10. But in the meantime, especially for our 5 parameters, the biggest thing that you need to know, and one of the biggest impacts that you'll have on your receive time as a sonographer, is that you should always use the least amount of imaging depth as possible. By reducing the imaging depth, you shorten the receive time, which means that the ultrasound machine can send out more pulses and get more samples of the anatomy as it's moving. I just want to remind you that this is kind of an introduction. We're going to keep building on these concepts, talking about why we make the decisions that we do, but these are the things that are really going to relate to the parameters in this chapter and some choices that you're going to start making as a sonographer, be it as a student or a seasoned sonographer. You're going to start to understand why you make the choices that you do. So let's go ahead and get into our 5 parameters. We're going to start with pulse duration. Now, the definition of pulse duration is the time it takes to complete one pulse. So pulse duration is going to be the amount of time it takes to just transmit the pulse. It's the on time. And because this is a time parameter, we are going to use a time unit. Typically, we are going to use microseconds because microseconds is derived from the period of the frequency, and the frequency is usually in megahertz. So we want to, again, make sure that we are using complementary units. The average value for pulse duration in ultrasound is 0.3 to 2 microseconds. Now, there really isn't a symbol for pulse duration, but you'll see it commonly abbreviated down to PD. And in our formula for pulse duration, we can see that pulse duration is equal to the number of cycles in a pulse multiplied by the period. Or we can calculate it as the number of cycles divided by the frequency. So when we look at our formulas and the way that they are set up, we can establish the relationships. Pulse duration is going to be directly related to the number of cycles in a pulse and to the time or the period of the wave. So if there are more cycles, our pulse duration time is going to be longer. If there's less cycles, pulse duration time is shorter. If the period is long, then the pulse duration is long. If the period is short, then the pulse duration is also going to be short. Now we also can see that pulse duration is inversely related to frequency, as frequency is the denominator, and the denominator and the quotient are inversely related. So if frequency is low, that means that the pulse duration is going to be longer or take up more time. And if the frequency is high, then the pulse duration is going to take less time. Again, if we have high frequencies, we have shorter periods. Shorter periods mean shorter pulse durations. Now, as a sonographer, you're not really going to have any impact on the pulse duration because it is related to frequency and period. We can't change frequency or period. We can't change pulse duration either because of it, and it will not be adjustable by you as the sonographer. Pulse duration is going to answer the question, how long does it take for one pulse to occur? Now this might sound really similar to period, but it is not the period of the wave. It is the period of the wave multiplied by the number of cycles, or it's the number of cycles divided by the frequency. So they're all related to one another, but this is not the period of the wave. It is the duration or the time it takes for the one pulse to occur. So using our two new formulas that we have for pulse duration, let's go ahead and look at an example over on the board and work through some of the math on it. Let's explore the two formulas that we just learned about pulse duration. Here we have a graph showing 3 pulses with 3 cycles each. Our two formulas, our pulse duration in microseconds is equal to the number of cycles divided by the frequency. Then we also have that pulse duration is equal to the number of cycles multiplied by the period. Taking a look at this wave and knowing that it's a 5 megahertz frequency, let's go ahead and figure out pulse duration using frequency first. So we're going to look at this formula. We have the number of cycles divided by frequency. When we are given a picture graph, all we need to do is count the cycles. We have 1, 2, and 3. So we have 3 cycles, and our formula says to divide it by the frequency in megahertz. The pulse duration for this graph is 3 cycles divided by 5, which gives us 0.6 microseconds. If we were to take out a stopwatch and watch this pulse go by, it would take 0.6 microseconds to do so. Using the same graphical representation of the wave and knowing that it's a 5 megahertz wave, we can use the period-based formula to calculate pulse duration. But this time we actually have to do a little bit of extra work. First, we have to calculate the period. We're told that the frequency is 5 megahertz. And we know that frequency multiplied by time equals 1, and that they are reciprocals. So with the 5 megahertz frequency, to figure out period, all we really need to do is move the 5 into the denominator position underneath a 1. So period will be 1 divided by 5, which actually equals 0.2 microseconds. Now we can take our period and multiply it by the number of cycles in the pulse according to this formula, and when we do that, we also get 0.6 microseconds per pulse. So again, it's the time of the pulse, that is the pulse duration. We're looking for a time unit to match up with it. So it works out either way. We can use period multiplied by the number of cycles, or we can use number of cycles divided by frequency, and we will still get the correct pulse duration no matter how you do it. And up next, we do have our answer to our pulse duration practice. In the pulse duration practice, you're going to get an opportunity to fill in some charts that are missing either frequency or period, and then you need to calculate what the pulse duration is based on the number of cycles provided. So here we have the answers to our pulse duration practice. How did you do? Well, remember to check all the areas that are highlighted in green. Those are the areas that you needed to fill out. If you feel good about all this and are ready to skip forward, go ahead and head to the next section. If you want to see this math worked out though, hang out. We're going to head back to the board. We're going to take a look through our pulse duration practice questions. In these questions, you are responsible for filling out the highlighted green areas based on the pulse duration formulas that we just learned. You have a chart with the number of cycles, frequency, period, and pulse duration to fill in with certain elements of the graphs completed. Our first graph offers us that there are 6 cycles per pulse in a wave that has a frequency of 2 megahertz. We need to figure out the period and the pulse duration. To figure out the period, we need to take the reciprocal of the frequency, and that will give us the period. So 1 divided by 2 megahertz gives us a period of 0.5 microseconds. So we can put in 0.5 microseconds in our period column. Next, we are going to use either the frequency or the period to figure out pulse duration. Because we had to calculate period, I'm going to use the period method so we stay consistent throughout the rest of the charts. To calculate pulse duration then, we need to take the period of the wave and multiply it by the number of cycles, which was 6, 0.5 times 6 equals 3 microseconds. So our pulse duration for a 6-cycle pulse with 2 megahertz frequency is going to be 3 microseconds. Let's look down then at the next example. This time we have 3 cycles per pulse with the 2 megahertz frequency. We already calculated our period at half of a microsecond. So now we need to figure out the pulse duration by taking the half a microsecond, multiplying it by 3, the number of pulses in the cycle, and that will give us 1.5 microseconds. So we can fill that part of our column in as well. The final question, and kind of the crux of the whole reason that we're doing these practices, is to understand the relationships. It's asking us what happened to pulse duration when the number of cycles decreased. So when we went from 6 down to 3, our cycles decreased. Note that our frequency stayed the same, our period stayed the same, but our pulse duration decreased. And that's because there are less pulses per cycle. The next chart tells us that both of the waves that we are going to be comparing both have 5 cycles per pulse. We need to calculate the frequency, we're given the periods, and then we need to calculate the pulse duration. Let's look at the top one. We're given 0.1 microseconds as our period. We know then that frequency has to be the reciprocal of that. So we're going to do 1 divided by 0.1. And 1 divided by 0.1 equals 10 megahertz. The frequency that complements 0.1 microseconds is 10 megahertz. Now we're going to switch over to calculating pulse duration, and this time I'm going to use pulse duration being equal to the number of cycles divided by the frequency. So we're told that our number of cycles is 5. We're going to divide that by the 10 megahertz. 5 divided by 10 equals 1/2. So our pulse duration is half of a microsecond in a wave that has 5 cycles per pulse at a 10 megahertz frequency. Let's switch to the bottom one. Again, we're told that we have 5 cycles in this pulse. We're told that the period then is 0.3 microseconds. Again, we just need to take the reciprocal of 0.3 to calculate the frequency. 1 divided by 0.3 is about 3 megahertz. We're going to round. So we can put 3 megahertz into our column. Now again, we're going to use our number of cycles divided by the frequency to calculate the pulse duration. So we have 5 divided by 3, and that is going to equal 1.6. So our pulse duration on a frequency of 3 megahertz with 5 pulses, with 5 cycles per pulse, gives us a pulse duration of 1.6 microseconds. And in this one, we're asking what happened to pulse duration when the period increased. So we are looking that our period went from 0.1 microseconds increasing to 0.3 microseconds. By increasing the period, we lowered the frequency because those are opposite, they're inversely related. And we see that with pulse duration, the longer period created a longer pulse duration. So we had 5 cycles for both. If the period for the top one is shorter than the period for the bottom one, then it stands to reason that the pulse duration is going to be longer when there is a longer period. We can say that when period increases, pulse duration increases. They are directly related. Let's take a look at the last chart. In this one, we have cycles per pulse and frequency given to us. We are again going to calculate the period and the pulse duration. So we need to calculate the period by taking the inverse or the reciprocal of frequency. For the top one, we will move 10 into the denominator position underneath the 1, and we will see that 1 divided by 10 equals 0.1 microseconds. And we can fill in our column with that time. We're then going to use the period-based pulse duration formula to calculate pulse duration. So we have 0.1 multiplied by 2 cycles in the pulse. 0.1 multiplied by 2 gives us 0.2 microseconds. Let's take a look at the bottom one. We now have 7 megahertz. We'll move the 7 into the denominator position. 1 divided by 7 equals 0.14 microseconds. So the period for a 7 megahertz wave is going to be 0.14 microseconds. We will take that 0.14, multiply it again by the number of cycles in our pulse or the chart. It is 2. 2 times 0.14 equals 0.28 microseconds. And underneath we're asking what happened to the pulse duration when the frequency decreased. So we went from 10 megahertz down to 7 megahertz. And when the frequency decreased, we see the period increase, and then we also see the pulse duration increase. So if the period increases, we're going to see the time of the pulse duration also increase. Section 4.3, spatial pulse length, is going to be our next parameter that we're going to learn about. The definition of spatial pulse length is the distance that a pulse takes up in space. So very similar to wavelengths, spatial pulse length are distance measurements. Now again, if we had a ruler, we could go and measure the length of the pulse, but again, there are formulas, so we are able to actually calculate the spatial pulse length based on certain parameters. Because spatial pulse length is a distance, we are going to use any distance or length unit. In ultrasound, we typically use millimeters, and in clinical ultrasound, we will see that spatial pulse length is usually between 0.1 and 1 millimeter in soft tissue. And yes, we are highlighting soft tissue again, because as you'll see in a second, spatial pulse length is related to wavelength. Wavelength was related to the medium, and therefore spatial pulse length is as well. Now we don't have really a symbol for spatial pulse length, rather a common abbreviation. You'll often see it as SPL. And we will see that SPL is equal to the number of cycles multiplied by the wavelength. So from this formula, we can see that spatial pulse length is going to be directly related to the number of cycles in a pulse and directly related to the wavelength of the cycles. If there are more cycles, the SPL will get longer. If there are less cycles, it'll get shorter. And if the wavelength is longer, then the SPL will get longer. And if the wavelength is shorter, the SPL also gets shorter. Now, because spatial pulse length is so closely related to wavelength, and wavelength is determined by the machine and the medium, so is spatial pulse length. An important feature that I've kind of already introduced you to is the fact that spatial pulse length is going to have a major effect on axial resolution. The shorter the SPL usually means the better the axial resolution, and the better the axial resolution means better the detail. So again, this just further illustrates why we really want the highest frequency possible, because high frequencies are going to have shorter wavelengths are going to produce shorter SPLs, and shorter SPLs improve our resolution. So spatial pulse length is going to answer the question, how much space does one pulse take up? We're going to head back over the board to use our new formulas that we learned and see some mathy examples on them. Now that we've learned a new equation for spatial pulse length, let's take a look at an example again using that new knowledge. This graph probably looks pretty familiar to the graph that we used for pulse duration, and in fact it is. It's another 5 megahertz frequency traveling in soft tissue, 3 cycles per pulse. This time though, we are going to calculate the distance of each pulse. So using our SPL formula, we see that it is number of cycles multiplied by the wavelength of the frequency. Because we have a picture to take a look at, all we simply need to do for this one is to count the number of cycles. We can count 1, 2, and 3. So the number of our cycles for this image is going to be 3 cycles. The next thing that we need to do is calculate the wavelength. If you recall back to our Unit 3 formulas, we know that wavelength then is equal to propagation speed divided by frequency. And because this is in soft tissue, we can expand that to be wavelength equal to 1.54 millimeters per microsecond divided by the frequency in megahertz. And in our example, we're told that it's 5 megahertz. If we do the math then, 1.54 divided by 5, we see that wavelength is going to be equal to 0.31 millimeters. We're going to take 0.31, plug it into our SPL formula, and what we end up getting is 3 multiplied by 0.31 equals 0.93 millimeters. So if we could get just a tiny little ruler out and measure our spatial pulse length, it wouldn't even be quite a millimeter given these frequencies and pulse parameters. And now that we're back, we're going to head into the practice for spatial pulse length. In the practice, you will be filling out a chart again, filling in the missing spatial pulse length, and then determining how some parameters will react based on the answers that you have found. Go ahead and pause, and when you're ready, unpause to see the answers. And here we are with our answers. So again, everything highlighted in green was your responsibility to fill out. And how did it go? If you understood the math behind spatial pulse length, please feel free to jump forward to our next chapter. Otherwise, hang around because we're going to head back to the board and go over these examples. To complete the spatial pulse length practice, we have again been given two charts to fill in with missing information. The first chart gives us the number of cycles per pulse, a frequency, and we have to calculate the spatial pulse length. Remember that spatial pulse length is equal to the number of cycles multiplied by the wavelength. So in both of these scenarios, we need to calculate the wavelength based on the frequency. Both of our examples give us a 2 megahertz frequency. So we are going to take wavelength being equal to 1.54 millimeters per microsecond divided by 2, the frequency in megahertz. 1.54 divided by 2 gives us 0.77 millimeters for the wavelength. To calculate the spatial pulse length of the top row, we are going to take the number of cycles, which is 6, and multiply it by our wavelength. 6 times 0.77 equals 4.6 millimeters. So we can put that into our chart, 4.6 millimeters. Now the next one tells us that we have 3 cycles in our pulse. Multiply that by the wavelength that we calculated. And 3 multiplied by 0.77 equals 2.3 millimeters. So let's go ahead and fill our chart in with that information. Now the question asks us what happened to the spatial pulse length when the number of cycles decreased. So we started at 6 and we decreased to 3. So when the number of cycles decreases, we see that the spatial pulse length will also decrease. This tells us that the number of cycles and spatial pulse length are directly related, and that when there are fewer cycles in a pulse, we are going to have a shorter spatial pulse length. The second chart in the practice tells us that we have 5 cycles per pulse, and this time we have 2 different frequencies, a 12 megahertz and a 6 megahertz, and we need to calculate the spatial pulse length. Again, the spatial pulse length is equal to the number of cycles in the pulse multiplied by the wavelength. So we're first going to figure out the wavelength for each of these frequencies. 1.54 millimeters per microsecond divided by 12 megahertz. 1.54 millimeters per microsecond divided by the 12 megahertz equals 0.1283. And 0.1283 multiplied by the number of cycles in our pulse equals 0.64 millimeters. So we can take that value and place it in our chart. Let's do the same thing for the 6 megahertz frequency. We'll take 1.54 millimeters per microsecond and divide it all by the 6 megahertz. Now when we do that, equals 0.256 millimeters, and we'll multiply that by the number of cycles in our pulse, and that will give us a total of 1.28 millimeters. So we can add that value to our chart. And now we can look at the question, what happened to SPL when the frequency decreased? So we see that the frequency got lower, and when we lower our frequency, we see that our wavelengths get longer. So we have a higher wavelength with a lower frequency. And because we have that longer wavelength, we then see that our SPL also increased. By showing this math, we are seeing that when we decrease the frequency, we increase the wavelength, and by increasing wavelength, we get longer spatial pulse lengths. So to review, up until this point, we had pulse duration, which is machine controlled and cannot be adjusted, and we had spatial pulse length, which is machine controlled and medium dependent and also cannot be adjusted. But now we have three parameters that are very dependent on depth. And because depth can be adjusted by you as the sonographer, you actually have a lot of control over these three parameters. So the depth dependent parameters include pulse repetition period, pulse repetition frequency, and duty factor. Now I want to highlight very, very important, pulse repetition period and pulse repetition frequency have nothing to do with the wave period and the wave frequency. So PRP and PRF have nothing to do with period or frequency of a wave. So when we look at a picture of a pulse wave like the one that you see on your screen, if we are looking at this in a unit of time, then we are able to determine what the pulse duration is and recall that it is determined by the source. If we look at this in the unit of distance, then we can define what the spatial pulse length is and recall again, this is by source and medium. So remember, neither of these parameters are something you can adjust as a sonographer. What you can change as a sonographer are the depth-dependent parameters. So when you change the maximum depth of the image that you are creating, you are going to change the receive time or the off time. And therefore, pulse repetition period, pulse repetition frequency, and duty factor will all change. Along the side of an image is a scale, and the scale is going to tell us the depth of the image. We typically see it represented as centimeters, and the maximum imaging depth is the bottom of the field of view. To change the maximum depth, there is a knob or toggle on the machine that will adjust the depth. In this image here, we see that the maximum depth is set at 3 centimeters. In this example, we can see that it goes all the way down to 5 centimeters. And in this example, we can see that the max imaging depth is more to about 16 centimeters. So when you increase or decrease the depth, you are going to change the PRP, PRF, and duty factor. Without getting too far into the physics, or at least the heavy duty part of the physics quite yet, when an image is created, what typically happens is that a sound pulse is sent into the body. And that sound pulse is going to travel through the soft tissue, sending back echoes about the reflectors that it interacts with. And the machine is going to wait to get all the echoes back from at least to the distance of where we have our maximum depth set. So if we have a 3 centimeter depth image, it's going to wait till the echoes from 3 centimeters make it back to the transducer. So one pulse, one waiting period, is going to create one scan line. And that one scan line is just one tiny little bit of the image. Once the information comes back from that first pulse, from the maximum imaging depth, then another pulse can be sent and processed. So we have to have a pulse, wait, wait, process, and display. Pulse, wait, process. Pulse, wait for it to travel, process, display the scan line. Pulse, wait, get all those echoes back, display the scan line. So this is happening incredibly fast. Much faster than we can clearly process with our own minds, because it looks like to us that the image is just always there. But again, the machine is sending a pulse, waiting for those echoes to come back, so it can process it and display each scan line till we make a full frame. And when we make the full frame, it starts all over again with the process and sweeps across, creating those scan lines to make the next frame. So the whole reason that PRP, PRF, and duty factor are all related to depth is because of that waiting period. The more depth there is, the longer the machine has to wait for those echoes to return before it can scan the next scan line or send the next pulse. So take a look at these two pictures. We're just going to wait, watch a few scan lines go through, watch a few images being made. Notice on the top one that we are scanning to a maximum depth of 15 centimeters. In the bottom picture, we're only scanning to a maximum depth of 7 centimeters. And so when we reduce the depth, we reduce the waiting time and therefore can produce more images. So if you watch long enough, you'll see that the 7 centimeter depth is creating more images than the 15 centimeter depth because there is less waiting time for that pulse to travel the 7 centimeters and come back. This waiting time is the whole reason why we want to use the least amount of depth as possible, especially for those of you that are imaging moving structures. We want as many refreshes as we can of our frame so we can get a very realistic representation of how the body is moving. So let's go take a look at our parameters. We're going to start with pulse repetition period. Pulse repetition period is the time from the start of one pulse to the start of the next pulse. So remember that pulse duration was only the actual time of the pulse. Pulse repetition period is going to be the pulse duration or the on time plus the off time or receive time. Remember, pulse repetition period has nothing to do with the period of the wave. It is 100% the time it takes to transmit the pulse and receive the echoes. Because this is a time parameter, we are going to be measuring this in microseconds or any other unit of time. As far as an average pulse repetition period, it is actually kind of difficult to say exactly what the average is because we can change the depth for whatever we need. So the time can actually vary quite a bit based on the depth that you have chosen to image at. However, it is usually somewhere between 13 microseconds if our maximum depth is set at 1 centimeter to about 260 microseconds if we have our depth set up to 20 centimeters. Again, pulse repetition period is not really represented by a symbol, but rather a common abbreviation, PRP. And we see in our formula that PRP multiplied by PRF equals 1. So PRP and PRF are reciprocals, but we also have another formula down there. PRP multiplied by 13 microseconds is going to be equal to the depth in centimeters. We are going to focus mostly on the reciprocal relationship between PRP and PRF for this unit, but when we get to unit 7, we're going to explore that other formula in a lot more detail. I did include it in this lecture, so you have it and you can put it on your formula sheet if you want to keep everything together. But again, we're going to cover that much more in a future unit. So from these formulas, I kind of already gave it away. Pulse repetition period is a reciprocal of pulse repetition frequency. If PRF is getting lower, then we're going to see that PRP is getting longer. So if that doesn't immediately sound like inverse relationship, remember if PRF gets lower, that means that the value, numerical value of PRF is going down, or the numerical value of PRP is increasing. The bottom formula then shows us that pulse repetition period is directly related to depth. That is why this is considered a depth-dependent parameter. If the maximum imaging depth is deeper, then our pulse repetition period is going to be longer. There's more waiting. If the maximum imaging depth is shallow, then our PRP is going to be short because there's less waiting. As a sonographer, you're going to have a huge impact on pulse repetition period, and you do this by changing the maximum imaging depth of the image. Shallow depths are going to reduce the PRP, where deeper depths are going to increase it. As a sonographer, you should always make sure that you are using appropriate imaging depth. That means to not have it too shallow where you're cutting important anatomy off, or have it so deep that we're practically imaging into the table. Balancing your depth is going to be very important for improving temporal resolution. Let's jump over then to pulse repetition frequency. Pulse repetition frequency is the number of pulses per second a system can send. So pulse repetition frequency is going to tell us how many times a pulse can be sent into the body per second. Remember back to the image where we were sending a pulse and then waiting for that pulse to travel to the maximum imaging depth, and then we could display our scan line. Well, if we can send pulses quickly, that means that we can display those scan lines very quickly, and therefore create a full image very quickly. But when we increase the maximum depth and make it really, really deep, we're going to make that waiting period longer, and therefore we can't send as many pulses, and it's going to take a lot longer to create the full image. Now, pulse repetition frequency is not the frequency of the wave, but it does share the similar definition in that we are talking about in events per second, and because of that, we do see that pulse repetition frequency is measured in a derivative of hertz, typically kilohertz in ultrasound. In clinical imaging then, the average PRF is about 1 to 10 kilohertz. Just like everything else, there's more of a common abbreviation, it's PRF, and so then we see that PRP and PRF multiplied together are going to equal 1, and PRF is going to be equal to 1 divided by PRP, again just expressing that they are indeed reciprocals of one another. And then just like PRP, I do have that other kind of fancy formula where PRF is going to be equal to 77,000 centimeters per second divided by depth. And again, we are going to cover that a little bit more in Unit 7 in much more detail and talk about why that is a formula that we have. Focusing on PRP and PRF being reciprocals, we see again that if the PRP gets longer, we will have a lower PRF. If the PRP gets shorter, then we should have a higher PRF. We can send more pulses out. We also see then too that PRF is inversely related to depth. Increase your maximum imaging depth, we're going to have a lower PRF. If you decrease your maximum imaging depth, make it shallow, we're going to have a higher PRF. And again, just like pulse repetition period, you have an immense impact on pulse repetition frequency, all by changing the maximum imaging depth. The shallower the depth the image is set to will increase our PRF, which means we can create more frames per second because we are sending out more pulses per second. If we increase our depth, we're going to start to see a worsening of our temporal resolution because we cannot make as many frames, because we cannot send out as many pulses per second. Let's take a little bit closer look at PRP and PRF and their relationship to one another. And I've already mentioned that they are reciprocals. So essentially, if one increases, the other must decrease and vice versa. And we know that if we have 5 representing the value for PRF, then PRP is going to be 1 over 5. We're going to move that 5 into the denominator position under a 1 to create the reciprocal. So that is very similar to period and frequency, but they are not the period and frequency of the wave. They represent the time for on and off pulses and the amount of pulses we can send per second. Remember that pulse duration is part of the PRP, so it is pulse duration, the on time plus the off time, but pulse duration is what it is. It cannot be changed. It's going to be set by the machine based on the transducer that we select. And when we change depth, it is actually changing the listening time. It doesn't change the pulse duration. It doesn't change the spatial pulse length. It doesn't change frequency or wavelength or any of that. The only thing that changing the depth changes is it changing the listening time. So let's take a look example at how PRP and PRF are related to one another and how they react to different depths. So let's say that these transducers are the exact same transducer. In the green situation, we have the transducer set to a 16 centimeter max depth. And in the yellow situation, the very same transducer has been reduced to an 8 centimeter max depth. So remember, these are the same exact transducers. So that means that the pulse duration, the frequency, the period, the propagation speed, the SPL, the wavelength, all of that's the same because these are the same transducers. The only thing that's different between them is that one is imaging to 16 centimeters, the other is imaging to 8. So in the green transducer, it has to image to a deeper maximum depth. Increase in depth, we're going to see an increase in PRP and a decrease in PRF. So it's going to have more depth, more listening time, less pulses per second. And we can see that visually comparing that to the yellow one, which is only imaging to 8 centimeters. That pulse is sent out much more quickly compared to the 16 centimeter pulse. So in the yellow transducer, we see that the depth is reduced, which means that the pulse repetition period is reduced. There's less listening time, which means we can send out more pulses per second. So of course, now that we have some new formulas, we are going to head over to the board to look at some of the math behind the formulas and to look at the example in the workbook. Just as we've been doing with all of the other new formulas that we are learning, we should go ahead and practice our new PRP and PRF formulas. For this unit, I've decided that I want you to focus more on the pulse repetition period multiplied by the pulse repetition frequency equals 1. And if we manipulate this and transpose it to solve for PRF and PRP, we'll see that PRF is equal to 1 over PRP, and PRP is equal to 1 over PRF. And that is all because of their special reciprocal relationship. So these three formulas are really going to help us for these two examples. The first example shows us a picture of a pulsed wave traveling in soft tissue. It is a 5 megahertz wave, and if we look at the graphical representation, we can see that there are 2 cycles per pulse. The question then is, what is the pulse repetition period and the pulse repetition frequency? When presented with a picture like this one, to figure out the pulse repetition frequency, it is simple enough as just counting the number of pulses that occur in 1 millisecond. So we have 1, 2, and 3 pulses within a millisecond. Using the millisecond time and knowing how to convert numbers, we can say that this is 3,000 pulses per second, or if we want to use values that are more applicable to pulse repetition frequency, it would be more appropriate to say that this is a 3 kilohertz PRF. To calculate PRP, then, we're just going to use the magic of reciprocal flip-flop. So we need to move the 3 down into the denominator position under a 1. 1 divided by 3 equals 0.33 milliseconds for PRP. Note that we are using complementary units for milliseconds and kilohertz for the PRP and the PRF. Now let's take a look at an example that increases the number of pulses per millisecond. This time we have 5 pulses. 1, 2, 3, 4, 5. So our pulses per second is 5,000 or 5 kilohertz. To calculate PRP then, we are going to divide 1 by 5, and that is going to give us 0.2 milliseconds for the PRP. In the bottom part of our paragraph, I actually was able to take it a little bit further with you, so if you want to follow along for the math, stick around for this part. We had those other 2 formulas. We had PRP in microseconds being equal to 13 microseconds multiplied by the depth in centimeters. And then we also know that PRF in hertz is going to be equal to 77,000 centimeters per second divided by the depth in centimeters. And the depth that we are talking about is the maximum imaging depth. So I'll show you an example in each of them how I was able to calculate that. On the top one, let's use the PRP formula. Now it's important that we have PRP in microseconds, but we calculated this to be 0.33 milliseconds. So we need to convert that to microseconds first. So 0.33 milliseconds is 330 microseconds. To get depth by itself, we need to divide by 13 on both sides. So we're going to take our 330, divide it by 13 microseconds, and that will equal our depth. 330 divided by 13 equals about 25 centimeters of depth. Let's go ahead and calculate the depth of the second one using the PRF formula. So in the last one, we calculated PRF to be 5 kilohertz. Well, 5 kilohertz does not match up with what we need for hertz. So again, we need to convert into the proper unit. 5,000 kilohertz is the same as 5,000 hertz. And to solve for depth, we are going to need to manipulate the formula again to isolate it on one side of the equal sign by itself. So if I multiply both sides by depth, that cancels that out, and then I can divide this side by PRF, divide this side by PRF, and now I have that depth is equal to our 77,000 centimeters per second divided by the PRF. So after our manipulation of PRF into hertz, we have 5,000 hertz. All we need to do is take that PRF and divide 77,000 by it. 77,000 divided by 5,000 equals about 15 centimeters of depth. So our top waveform shows us that we are imaging to a maximum depth of 25 centimeters. We can see long wait times that match up with the idea Deeper depth equal longer pulse repetition periods, which decrease the pulse repetition frequency. Fact checking the bottom one then, we can see that our depth has decreased, so it makes sense that we are able to have a higher pulse repetition frequency and shorter PRPs. The very last bonus question on this page then asks us, can we figure out what the pulse duration is for these waves? Well, remember that pulse duration is equal to the number of cycles divided by frequency, or the number of cycles multiplied by period. And we're told in the problem that the frequency is 5 megahertz. So we can count our cycles, which is 2, and divide it by 5, which was our frequency in megahertz. 2 divided by 5 equals 0.4. When we're talking about pulse duration, so we are going to label this microseconds. So 0.4 microseconds of pulse duration is the same for both of these waveforms. That is not going to change. That is a constant based on the frequency or the period of the wave. It has nothing to do with the depth and the PRP and the PRF. So we're going to keep this value in our back pocket because we're going to need it for when we figure out the duty factor. We do need to finish up our depth-dependent parameters, and our last one is duty factor. Now, duty factor is the percentage of time that the machine is transmitting. Remember that in pulse wave ultrasound, there's an on time and an off time. So duty factor is going to be the fraction of the on time divided by the on and off time put together. So it's the pulse duration divided by the pulse repetition period. Pulse duration is just the on time. Pulse repetition period is the on time and the off time. What this ends up doing is helps to quantify the amount of time that a patient is actually being exposed to ultrasound energy. So they're really only getting it during the pulse, which is a very, very small fraction of time. But the duty factor tells us what that fraction or percentage is. Way back in Unit 1, we talked about units, and we said that every numerical value that we have should have a unit associated with it, millimeters, centimeters, whatever. Well, we've just come across our first parameter that we're okay saying that this is a percentage. Now, a percentage is not technically a unit, but it does fill the role of describing the number because it's telling us how much of a whole this number is. When we're imaging with B mode or grayscale, the average value of duty factor is going to be less than 1%. So that means it's just this little boop, and then the rest of the time it's just listening. And it's listening for those echoes to come back. And then another quick little pulse, and then it waits. So it's talking far, far less than it is actually listening for echoes to return. When we turn on different parameters of the machine, like using Doppler, it actually has to talk a little bit more to get a little bit more information. And it also uses longer pulse durations or longer spatial pulse lengths. And because of that, that's going to increase the amount of talking time compared to listening. So we'll see an increase from about 1 to 10% when we turn on Doppler. Continuous wave ultrasound is talking constantly. And continuous wave ultrasound then has a duty factor of 100% because it never stops to listen, it's always talking. And that's why it can't create an image. Like our others, we have common abbreviation for duty factor. You'll often see it as DF. And in our formula, we can see that duty factor represented as a percentage is equal to the pulse duration divided by the pulse repetition period. To turn it into a percentage, we do need to multiply by 100. It is also appropriate to leave duty factor as a decimal if you wish. The other big part of the formula that I want to point out is that you see pulse duration and pulse repetition period are using the same unit. You must have the same unit in those value places so that the units cancel each other out and we get an actual percentage. And the formula again will give rise to the relationships that we see. So we have duty factor being directly related to pulse duration. If we have a long pulse duration, that means more talking time, we'll see that the duty factor increases. If the pulse duration is shorter, then we'll see that the duty factor decreases. Duty factor then is inversely related to pulse repetition period. When there is more listening time with the pulse repetition period, we'll see that the duty factor decreases, which makes sense. If we're just getting a small little blip and then lots of listening time, the percentage or fraction that the machine is talking is very low when the PRP is long. However, if we have a very long pulse or a lot of talking and just a little bit of listening time, we're going to see that that duty factor starts to increase. It's taking up more of that time, increasing the percentage that it's on. Unlike PRP and PRF, duty factor does have some relationship with pulse duration, and pulse duration is determined by the machine, so technically duty factor is also determined by the machine. But we can change the duty factor by changing the depth, and that is because of its relationship to pulse repetition period. So of course we've learned yet another equation, so we are going to head over to the board to discuss the example that's in your workbook and work through some of the math. All right, we made it to our last parameter example, and we've been using the same example, kind of building on it. So we saw with PRF and PRP how to calculate both of those values based on the information that we have from these images. And we have already calculated those, and I've included that on the side here. But this example is going to take a look at how to calculate duty factor. I've provided the duty factor formula in the corner here for us. We're going to use that in a minute. To calculate the duty factor of either of these waves, we first need to know what the pulse duration is, and then we can divide it by the pulse repetition period. Because this is the same example that we use for PRP and PRF, we've already calculated pulse repetition period. The top waveform has a pulse repetition period of 0.33 microseconds, and the bottom one has a PRP of 0.2 microseconds. The piece of information that we're missing, though, is the pulse duration. So we need to calculate the pulse duration. If you stuck around from the last example, we calculated pulse duration using this formula, number of cycles divided by the frequency. We can count the number of cycles in each pulse to be 2, and we're told that the frequency is 5 megahertz. 2 divided by 5 equals 0.4 microseconds. But there's a really big red flag that we need to take care of. We do not have matching units for these values. So we either need to convert pulse duration to milliseconds, or we need to convert pulse repetition period to microseconds. Instead of converting both of the PRPs, which are separate values, into microseconds, I'm going to convert the pulse duration into milliseconds because it is the same value for both of the waves. 0.4 microseconds into milliseconds equals 0.0004 milliseconds. Now we can divide that by 0.33 milliseconds, and 0.004 milliseconds divided by 0.033 milliseconds and gives us a value of 0.0012. And we can stop here if we wanted to. It is okay to express duty factor as a unitless decimal, but it's more accurate, and you'll see it more commonly in your books and in your tests, to present it as a percentage. So to finish this off, we do need to multiply this by 100, and the final duty factor percentage of the top pulse is 0.1%. We can do the exact same thing for the bottom pulse, convert 0.4 microseconds into 0.0004 milliseconds, divide it all by 0.2 milliseconds, and we get a value with that one of 0.002. Again, we can leave it as a decimal if we want, but to convert it to a percentage, we need to multiply by 100, and when we do so, the duty factor of the bottom wave is 0.2%. To finish up this unit, then, we are going to go over a summary of everything that we've talked about, and I do have some practice problems that will include a bunch of the new formulas that we just learned and kind of put it all together with the last unit. So here I have an example of a pulse wave, and we're going to say everything that we describe on the top is time, and everything we describe on the bottom is going to be related to distance. Now remember, we had those 7 parameters that could describe both continuous and pulse waves. So we have our wavelength, which is equal to the propagation speed divided by frequency. We have period, which is 1 divided by frequency. And then not shown on this graph, we do have our frequency, which is 1 divided by the period. Also not shown on this graph, but related to the parameters that can describe continuous and pulse wave then, is propagation speed. And we know that in soft tissue, propagation speed equals 1.54 millimeters per microsecond. Also not shown on this graph are amplitude, power, and intensity, but they can all describe continuous and pulse waves. This unit, we learned about the 5 parameters that can only describe pulse waves. And so with that, we have spatial pulse length, which is the wavelength multiplied by the number of cycles. We have the pulse repetition period, which includes the on and off time and is the reciprocal of the pulse repetition frequency. We have the pulse duration, which is the period multiplied by the number of cycles. And those two factors together are going to help us to calculate the duty factor of the pulse wave. And then we know that how many pulses can be sent per second is the PRF, and we can calculate that as a reciprocal of PRP. Remember that pulse duration is related to time of the pulse, and we want shorter pulse durations to create better images. We're going to see that short pulse durations come along with few cycles in the pulse or short periods, where long pulse durations are going to have many cycles in the pulse or longer periods. Spatial pulse length describes a distance, and we want short spatial pulse lengths to improve our images. By having shorter SPLs, we are going to see fewer cycles in the pulse or shorter wavelengths creating that pulse, where longer spatial pulse lengths are going to have many cycles in the pulse or be created from long wavelengths. Next, we have how all of our depth-dependent parameters are related to shallow imaging versus deep imaging. So when we have a shallow maximum image depth, we are going to see that we have less off time. There's not going to be as much listening happening. So because of that, we're going to see short pulse repetition periods. With short pulse repetition periods, we are going to see high pulse repetition frequencies. And because there's more talking, that means there's a higher duty factor. Compare that then to deep imaging, where there's more off time, so there's more time to listen. We're going to get a longer pulse repetition period because of that. And because we have more waiting time, we can't send as many pulses, so we have a low pulse repetition frequency, and because there's not as much talking, we end up lowering our duty factor. And speaking of duty factor, when the machine is off, our duty factor is at 0%. There is no sound being transmitted. There is no fraction of on time. When we are in 2D imaging, that means getting those grayscale images, our duty factor is less than 1%. It's doing much more listening than it is actually doing with talking. When we start to turn on color or turn on our Doppler imaging, we are going to increase our duty factor because these spatial pulse lengths become longer. There's more talking time to create Doppler images. So we up our duty factor to about 1 to 10%. Lastly, continuous wave ultrasound is going to have a duty factor of 100%. And that's a really big one. Continuous wave ultrasound has a duty factor of 100% because it is always on. There is at no point a time that it'll stop and listen, and that is why continuous wave ultrasound cannot create images. So one more final summary of all the 5 parameters of the pulse wave. We have duty factor. It is controlled by the machine, and it's going to change when the depth changes. Also controlled by the machine are pulse repetition period and pulse repetition frequency. They are reciprocals of one another, and they are going to be greatly affected by the maximum imaging depth. Next, we have pulse duration, which is controlled by the machine and cannot be adjusted. It is very innate to the transducer itself. The machine decides how many pulses will be used, and the pulse duration is going to be equal to the number of cycles multiplied by the period, or the number of cycles divided by the frequency. And lastly, we have spatial pulse length. Much like wavelength, spatial pulse length is also determined by both the machine and the medium in which the wave is traveling. So up next, we have the answer to practice number 1 from our summary practice problems. Now this practice number 1 is kind of a tricky one, and that's because we are figuring out pulse duration, PRP, PRF, frequency, propagation speed. We're going over all the concepts that we've talked about in the last couple units and kind of putting them all together based on knowing the frequency of the transducer and a picture of the pulse. So see what you can get through on your own, and then unpause the video and let's double check your answers. And here are the answers to practice number 1. Remember, you're filling in all of the green areas, and if you understand the math behind all of this, please feel free to jump ahead to the takeaway portion for practice number 1. Otherwise, stick around and we're going to go through all the math of how we figured these out. So let's head over to the board so we can take a look at all those formulas and fill out that chart completely. If you were able to calculate all of the practice number 1 pieces that we were missing, congratulations. That was a lot of work to go and find all those formulas and put them all together. and make some sense of this very little information that I've given to you. But the really cool part about this is that we can figure out so much based on just a few parameters. So it's actually really neat that it all kind of works out and we can do the math for all of this. And if you weren't able to figure it out, that's okay. We're going to go through it now, and I want to show you how it all works together. And you're going to have another opportunity in the activities section to try another one of these fill in the charts. Let's review really quick what we've been given. We've given a picture of a wave, and each of these represents a pulse. So let's go ahead and count those right now. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 pulses occurring over 1 microsecond. We're also given a zoomed in view of one of the pulses, and we can see on there that there is 1, 2, 3, 4 cycles within that pulse. Looking at the chart then, we're told that we are imaging to a max depth of 10 centimeters and that the frequency of this wave is 5 megahertz. So we have to figure out all the rest of this stuff. Well, just looking through some of these, we can figure them out very quickly. We're told that this is traveling in soft tissue, so we know our number for soft tissue and we can fill in our constant speed of 1.54 millimeters per microsecond. Also glancing down the list here, number of cycles per pulse, we counted that earlier, so we can fill that value in as well. Looking at some of the other factors that we can fill in, we know that PRF is the number of pulses per second, and in this case we already counted that. We got 8 pulses per 1 microsecond, which is the same as 8 kilohertz. So it's probably about all we can fill out just by kind of looking at things and not doing too many calculations. So let's go ahead and start with period and kind of work our way down with the calculations using the formulas that we've learned. Starting with period, we know that the period is the reciprocal of the frequency. If the frequency is 5 megahertz, then we just need to take 1 divided by 5, and that will give us a period of 0.2 microseconds. Next down on the list, we have wavelength, and we are told that this is traveling in soft tissue. We have the frequency, and we know that wavelength is equal to the speed of sound divided by the frequency in megahertz. 1.54 millimeters per microsecond divided by 5 is going to give us a value of 0.31 millimeters. So again, we've been working with these formulas. We know how to do this. We just have to take the time to figure out the pieces and plug our numbers in. Our next value down is the PRP. You can just use the reciprocal of the PRF. So 1 divided by the 8 kilohertz PRF gives me a pulse repetition period of 0.125 milliseconds. Next on our list then, we have pulse duration. Now pulse duration had a couple formulas for it. We could do number of cycles divided by the frequency of the wave, or we could do number of cycles multiplied by the period of the wave. And we already calculated both of them. We have the 5 megahertz and we have the 0.2 microseconds. For ease, I'm just going to do the number of cycles divided by the frequency. So we will get 4 number of cycles divided by 5, the frequency, and that is going to give us a value of 0.8 microseconds. Next on our list, we have the spatial pulse length, the number of cycles multiplied by the wavelength. And we've already calculated the wavelength out, and we've counted our cycles, so we can simply plug in our numbers. 4 for the number of cycles multiplied by the wavelength, and 4 times 0.31 gives us a value of 1.24 millimeters. Now we just have one last parameter to calculate, and that is the duty factor. And duty factor is equal to the pulse duration divided by the pulse repetition period multiplied by 100, so we can present it as a percentage. So pulse duration has already been calculated. We did that at 0.8 microseconds, and we've already calculated the pulse repetition period to be 0.125 milliseconds. But like our example earlier in the lecture, we can't have microseconds and milliseconds. We have to convert one of them. This time I'm going to go ahead and convert my pulse repetition period from milliseconds into microseconds. So 0.125 milliseconds into microseconds equals 125 microseconds. Now we can take 0.8 and divide it by 125 microseconds, and that is going to equal 0.0064. Multiply that by 100 so we can get our percentage, and our duty factor is going to be 0.64%. I hope you are able to follow along. It is a lot of math, but we got to use all those formulas that we've been learning, and now we're going to compare 10 centimeters max depth to 5 centimeters max depth and see what happens. So I copied all of our values into the first part of the chart, and now we're going to work on the second part of the chart. Now I'm going to give you a little secret here. The only values that could change based on depth are PRF, PRP, and duty factor. All the other values are going to be exactly the same because they have no relationship to the depth of the machine. This really shows us that it's important to understand the relationships between the different parameters so you can discuss how if one thing changes, another might change or it might not change. Let's go ahead and finish up the chart by calculating our PRF, PRP, and duty factor. Instead of going through the math on all of these, I'm going to show you another shortcut to finish out this chart. Remember that when we decrease our depth, we are going to see an increase in PRF, a decrease in pulse repetition period, and an increase in our duty factor. We have gone from 10 to 5 centimeters. So 10 divided by 5 equals 2. We are decreasing by a factor of 2. So if we decrease the depth by a factor of 2, that means that PRF is going to increase by a factor of 2. PRP will decrease by a factor of 2, and duty factor will increase by a factor of 2. So we can take the values that we've already calculated and apply our factors. 8 kilohertz times 2 is 16 kilohertz. We've increased it by a factor of 2. When pulse repetition period has its factor applied, it's divided by 2. So 0.125 divided by 2 makes our pulse repetition period 0.0625 milliseconds. And lastly, for depth decreased by a factor of 2, duty factor is going to increase by a factor of 2, and 0.6% multiplied by 2 is 1.2%. Now, as I mentioned at the top of the practice, this is most likely way more math than you are ever going to need to do. And I know that I kind of keep bringing this up, that we are really diving into the math, but my goal is to show you how that math affects the basics of physics. So in my experience, a lot of students think that they don't know how to do math or think that they're not comfortable with the math part of it. But then when I show them the math, the physics makes more sense. And so if you are the type that wants to memorize, this is why we always come back to our takeaways. If you want to memorize this information, that is completely up to you. But my ultimate goal is to make sure that you also understand, which is why I really like to show you the math behind the physics as well. So the takeaways that I want you to get from practice number 1, we have parameters that do not change with depth. That was basically what was happening in that. We had depth set at 10 centimeters and then we changed it to 5 centimeters. And the goal was to see what did not change with depth and what did change with depth, and then how did it change. Parameters that do not change with depth are going to be our frequency, period, propagation speed, wavelength, number of cycles per pulse, pulse duration, and spatial pulse length. Those are not depth dependent features. The ones that do change with depth are going to be PRF, PRP, and duty factor. And the next step that you need to look at is what happened when we changed the depth. So in our example, we went from 10 centimeters to 5 centimeters, or we decreased depth by a factor of 2. Remember that decreasing by a factor of 2 means to divide by 2. So when we decreased depth by a factor of 2, we saw PRF increase by a factor of 2. We saw pulse repetition period decrease by a factor of 2, and we saw duty factor increase by a factor of 2. Now we not only are able to represent the relationships that we see between depth but also express how they are proportionally related as well. As an example test question here, I have a sonographer is imaging at 10 centimeters and increases the depth to 20 centimeters. What happened to the pulse repetition period? So this question is asking you, do you understand how imaging depth affects the image, and specifically, how does it affect pulse repetition period? So your choices are doubled, halved, stayed the same, or that depth is not related to pulse repetition period. And in this case, the correct answer is doubled. The depth doubled, increased 10 centimeters to 20 centimeters, so it increased by a factor of 2. And because depth and PRP are directly related and proportional to one another, we'll see that the PRP also doubles in that case. So the correct answer is A. I know practice 1 was a little beefy, but we do have one more practice, and this is going to focus mostly on duty factor. There's just 2 waveforms, and you'll need to determine the duty factor based on the graphical representation of each pulsed wave. Go ahead and unpause when you're ready for the answers. And here they are. We have 2 waves that are being represented on these graphs. The graphs have dashes on them to represent an equal unit of time. And you've been asked to figure out what the duty factor is. Well, the first one has no off time. So we should immediately know that when there is 0 off time, that is a 100% duty factor. There is no listening. The fraction is 100%. It's always on. The bottom one, however, is a little bit tricky. Remember that duty factor is pulse duration divided by the pulse repetition period. So that's on time divided by the on and off time. So in this example, we have the on time here, off time, and the start of another pulse. And why this is a little bit trickier for a lot of people is they want to look at these spaces in between. They want to say there's 4 of them and somehow say that this is 25% duty factor. But that's not true. Because remember, pulse duration is the on time, and pulse repetition period is 1 unit of time, 2, 3 units of time. Start of one pulse to the start of the other pulse is the definition of the pulse repetition period. So we actually just kind of want to cover this one up, get rid of it. That's not part of figuring out duty factor. We're only looking at the pulse duration and the PRP, which is on time and off time to the next pulse. So we take the pulse duration, which is a unit of 1, and divide it by 1, 2, 3, and we'll see that the duty factor of this example is 33%. And that'll bring us to the end of Unit 4. So make sure that you are going through the activities in the workbook and take a look through the nerd check. Make sure that you are familiar with what the questions are asking. Make sure that you know how to define all of the parameters that we've talked about, the units that they are represented in, common symbols or abbreviations that they use, formulas that are related with the parameters, the relationships that those formulas represent, and then what your impact is on that parameter. Can you adjust it? Where is it created if you can't adjust it? What else is affecting it? Is it the machine? Is it the medium? What affects it? There are plenty of charts in the workbook and in your readings. I suggest that you take a look through those. Those might be really helpful to organize all this information in a very digestible way.